So welcome to the lecture. We will now start discussing relativistic index or component notation, and this will pave the way for tensor analysis. So let's first start with the Lorentz transformation law, which takes the following form. And note that, as we discussed many times in previous lectures, that we can denote this coordinate 4 vector by a column, and this is the 4x4 matrix. Now we will write this equation in terms of component form. So we can do it easily. So we can denote the coordinate 4 vector by x mu. So mu takes values 0, 1, 2, 3. And naturally, this is the column vector, and so mu denotes each of its row. So then the column of lambda will be multiplied with this row, denoted by mu. Then there is a row which is denoted by nu of lambda. Hence, the index on x prime mu will be nu. So note that this index that is repeated is summed over. We called it contracted index or dummy indices, and you can relabel them at any point of subsequent calculations. We will do that. We will freely relabel these indices which are summed over. Okay? Please keep that in mind. Now, when we write this equation, we have secretly assumed that the space-time coordinate, the origin of that, are coincident at these two frames. But there can be a constant shift between the origins. So in general, we can add constant shift, denoting them by a vector, constant vector, the components of which are m. These are known as translations. Note that, as we discussed last time, that we will mainly focus on the proper orthogonal Lorentz transformation. That is, the Lorentz transformations consist of only boost and rotations. So in 3+1 dimension, there are 3 boost and 3 rotations. So total 6 of them are there. And plus, if you include these 4 translations, so that there are 10 transformations, and they constitute something called a Poincare group. In fact, all the elementary particles are irreducible representation of the Poincare group. Next, we will work with differences or differentials, which is of the form d mu mu. So if we work with the differential, then this constant shift drops out. So we don't have to bother about these translations, and we only work with the Lorentz transform. And now from this, it follows delta So you can see that this is nothing but the Jacobian matrix when we do a coordinate change from x to x prime. And now you can see why our convention about the indices of Lorentz transformations natural, because this denotes the row of the Jacobian matrix. So this upper index denotes the row, and the lower index denotes the column. So Lorentz transformation is nothing but a Jacobian matrix, and we will later see that in the second half of the course, we will deal with the general coordinate transformations. And then instead of this Lorentz transformation matrix, we will get some general matrix, general Jacobian matrix, which will be a function of the space-time coordinate as well. Remember, this lambda, the Lorentz transformations, is independent of space-time coordinate. It's only a function of this boost or rotation. Like a Jacobian Now remember that these coordinates are independent of each other. So if we evaluate this, let's take the coordinates at the prime frame. Now what are these? So you can see at various x primes are independent of each other, then this will be 1 when mu equal to nu and 0 otherwise. And what that nothing but component of identity matrix denoted by E. Right? This is the Kronecker delta. Now let's use the chain rule for this side. If we do that, it's mu prime and you give the chain rule, and if you look at it carefully, this is nothing but the Lorentz transformation mu lambda times prime mu. There is a typo prime here, which is equal to this delta mu nu. Now, from the definition of inverse, we know that lambda inverse should be identity, and in terms of component, then this is row, this column of lambda, it will be multiplied with the row of lambda inverse, the nu, and component of identity is nothing but the Kronecker delta. Mu delta nu. So mu equal to nu, it's 1 or otherwise, right? So the corresponding matrix is identity matrix. Only diagonal elements are 1 and of diagonal elements. And then if you compare these two, then you can see that lambda inverse nothing but in terms of component takes this form. Okay. So this is the inverse Jacobian. And this is a very useful expression that we're going to use many times. Now, equipped with this, let's try to discuss the notion of vector. So the viewpoint that we'll adopt in this course is that these vectors, or more generically we will see for tensors, they are a local object. They are defined only around a point in the space-time manifold. So usually when you do the tensor analysis in R3, there is a global notion is attached with these quantities, but you will see in the later half of the course when we will do more differential geometry, we see that this global notion is actually not very useful unless otherwise you are working in flat space-time, but we will work in general in a curved space-time. So we will treat this object as a differential operator. We'll discuss it more in the second half of the course, but at this point, let's briefly sketch the main idea. So let's consider a function phi of x, and also let's consider curve, the Minkowski space-time, 0 is the curve, and the curve is parameterized by this way. So the 4 coordinates are function of some parameter lambda. Lambda is a real. Okay. Now we ask how this function changes over this curve. So what we have to do to compute that? So we have to calculate the directional derivative of this function. D of phi around x mu nu, but we wanted to compute the change of this function over the curve. So this x mu nu is a function of lambda to denote that considering the change over the curve, and t lambda. So this is the nothing but the directional derivative. Now we know that the phi is implicit function of lambda through the coordinates, and we use the chain rule to get the following: x mu lambda del x mu acting on this function. Okay. Now from this we can identify that it's nothing but the tangent vector defined at every point on the curve acting on this line along the curve. T mu nu del mu nu. So writing these as a short notation using just del subscript mu. We are going to use that. Now one can identify that this T mu nu is nothing but the component of the tangent vectors. T mu defined at every point on the curve. Now, if we pick a point P on the curve and consider all possible curves that is passing through this point and collect the tangent vectors for each of these curves at the point P, then we can show easily then the set of all possible tangent vector to all the curves that pass through this point P constitute a vector space. And we know that is nothing but the tangent space. And the element of that vector space are denoted by V, which have a component P mu and a basis vector del. The component basis. So in general, we could have used a more generic form of a basis, which we denote by E hat mu. But most of this code, we will focus on the coordinate basis. E mu. and this is the element vector space which lives at the tangent space at every point on this. So the bigger lesson is that we will consider vectors as a differential operator which lives at the tangent space associated with the every point in the Minkowski space. Okay. And we will denote that space or the vector space by T subscript P. P denotes that particular point. T subscript P denotes the tangent space at that. So each point in the Minkowski spacetime is equated with the structure of the vector space. And the elements of the vector space take this, right? Now we know that vectors corresponds to some physical quantities, and according to the principle of relativity, this should remain same in any inertial reference frame. So if you have V then mu at a particular frame, it should be equal to V prime mu at some other inertial frame where the component form some V prime in the basis del mu prime. Now act both sides by x prime alpha, you will get now what is this? So this is nothing but del x prime alpha x prime mu, and this is we just defined as Kronecker delta. Now what is this actually? Del alpha del x mu. Then what you can do, you use the chain rule to make this x prime. So del x alpha del x prime mu del x prime mu x mu, chain rule. Please do that, and if you simplify, then you will get the following. E prime alpha alpha mu g mu. Please do this intermediate step. You will get this. Then we can identify this is nothing but the Lorentz transformation alpha mu g mu, and this is the defining relation for the vector, that is these are the quantities whose components transforms by this equation under Lorentz transform. In literature, these are sometimes known as contravariant vector, we will simply call them vector. Now from linear algebra, we know that given a vector space, we can associate a dual space to that by defining a suitable map. So let's consider the following map omega, which takes a vector to produce a real number. And this map we also demand to be a linear map, that is linear combination two vector alpha 1 e1 and alpha 2 v2. Both alpha 1 and alpha 2 are some real number. This will give the following. And then this is going to give you real number. So as a whole, this is a real number. This is a linear map. And if you consider all possible linear maps from vector v to a real number, it again constitute a vector space, and we call them as a dual space. And if you are considering the vector as a tangent space, then this dual space will be the cotangent space, and this omega will be an element of that cotangent space or the dual space. So the element omega we can write again in terms of a component and a basis vector of this dual space. So omega, this is a component, and this theta that denote the basis of this dual space. So now we will work with a particular dual basis which satisfy this following relation. That dual basis takes the basis vectors of the tangent space mu, gives us a now if you work with this, and let us remind that these are just some number, they should be remain true any inertial reference frame. So frame that means irrespective of whether you are working in prime or unprime frame, relation will hold true. So now this map we have defined as a linear map. Also, we'll work with the coordinate basis, which means that this and you can write the del nu prime as del alpha nu x alpha. So let's put it here. Get mu x alpha mu alpha. Okay. Now these are nothing but element of these Jacobian matrices. They are just number for our case, and because it's a linear map, it will just come out. We'll have let's and this is equal to. Now, if this has to be true, then the following thing that I'm going to write down better be true. So we have mu eta mu alpha nu. So now again we can use some chain rule and invert this relation. So we can bring all these factor of this Jacobian matrices to this side by using chain rule. For example, we can use the fact that del x mu by del x mu del x alpha by del x prime nu, and this is nothing but del x alpha del x mu equal to Kronecker delta. Please use this, and then we can easily show that eta alpha del x alpha x mu. So we have derived the transformation property of the basis of this dual vectors, and you can identify easily that nothing but eta nu. Now we will going to use this transformation rule to derive the transformation rule for the component of these dual vectors, just like what we have done for the component of the vectors, and we'll see how the component of the dual vectors transform under Lorentz transformation, and that will give the defining relation for these dual vectors, which are also sometimes known as covariant. So again, let's do the following, that these dual vectors will correspond to the some physical quantities. So omega will remain same in inertial reference frame. So omega prime mu prime would be equal to omega mu theta mu. Okay. Now, if we do that and plug in the previous relation that we derived for the transformation law of the basis vector, then we get the following. Mu del Okay. Then this will imply that omega mu prime omega mu, and then you can again use chain rule to invert this relation. Please do that exercise. You will be able to get the following: Lx mu Lx prime mu omega. And now you can see this is nothing but the components of the inverse Lorentz transform. So we have the following inverse let's write it once again. The component of the dual vector transforms under the inverse Lorentz transform. In contrast, the component of the vector transforms under the Lorentz transform. And we called them covariant vectors, or we will use modern terminology, we will simply call them a one form. Now we will discuss one last thing. So remember, we are working in coordinate basis. So there is a natural choice for the basis for the vectors are del mu's, right, that we discussed. So now can we identify what these theta mu are if we work in coordinate basis? So before that, let me make one remark. So if you considering the dual space of the tangent space, it is also known as cotangent space, and then these one forms are the elements of the cotangent space. So we have derived the transformation law for the basis vectors of this one form, nothing but now remember that the coordinate differential transforms under Lorentz transformation in the following way. Then we can identify this theta with this coordinate differential. And remember that we are working with the particular choice such that theta mu and E mu delta mu. So then this gives the following if you work in coordinate differential: gx alpha beta alpha. At this point, note that this is not an equation but a definition of the dual relationship between the respective coordinate bases for a vector and one form. So we will end here, and in the next lecture we will generalize these facts for a generic rank tensor and see how it transforms under Lorentz transformations and so on. Thank you for listening.